Hello, my name is Lorenzzo Mantovani. I'm a graduate research assistant at the AVS laboratory at the University of Colorado Boulder, and today I will present the work intent sharing for emergent collaboration in autonomous Earth observing constellations. So first I will talk about the multi-agile Earth observing satellite scheduling problem. We can break it down in some parts. So the Earth observing satellites, basically satellites carrying sensing instruments in low Earth orbit in our case. Scheduling problem refers to finding the best sequence of actions to achieve our goals. Agile is because the satellite can maneuver about and along track, and we have multiple agents, multiple satellites in our system. So we define the problem as the joint objective to maximize the cumulative value of unique imaged targets. So we want to image as many targets as possible, but we also want to image targets with highest priorities. So the priorities, they vary from 0 to 1. Initially, we have a list of unfulfilled target requests, and if the target is imaged, then it is removed from this unfulfilled list and is added to the fulfilled list. Some previous work added communication between single-agent trained satellites, trying to reduce the number of duplicate images, reduce the duplicate effort, but in some cases the results were not satisfactory. So in this work, we are introducing a novel method to generalized satellites operating with asynchronous variable intervals, and also the intent sharing communication method that is considered to reduce the duplicate effort, number of duplicate images. So how did we formalize the decision-making problem? We used the decentralized Markov decision process, an MDP, where we defined state space as the combination of the state space of individual satellites and the environment. Similarly, the action space is the combination of the actions of each satellite. And we have rewards. So the satellite will receive a reward if it images a target from the unfulfilled list, and this reward is proportional to the target priority, and it will receive 0 reward otherwise. We are also working with variable decision interval, so the satellite will pick another action if it completes a task, if it misses the opportunity to image a target, and also if it reaches a defined step duration. Talking about our simulation environment now. We are considering 5 satellites in a formation flying configuration, and first in a long track configuration, as this image here is illustrating, where we are varying the true anomaly of the orbit. We are also considering a cross-track formation, where we are varying the longitude of the ascending node. Each satellite can pick one of 33 actions, that is charge, or image the upcoming next 32 targets. We also introduced power constraints, so the satellite must keep a positive power balance, and it consumes energy to image a target and to maneuver. We also introduce some information to the decision-making algorithm. Part of this information is for the satellite to know its relative position and velocity. Part of this information is about the training environment, information about the targets, and charging. We are considering 2 distinct target distributions, uniform distributions across the globe, that's what we are showing on the first row, varying the number of requests from 100 to 10,000, and also city-based on the second row, where the position of the targets are based on real cities, and here we are varying from 3,000 to 300 to 3,000. So here is a visualization of the simulation. We have 5 satellites in a cross-track formation. They will extend lines to reach the targets. Basically, it shows that they are intending to image those targets, and once they are in the circular region, they will be able to perform that action. We are using the Gymnasium API. It's a widely used tool for reinforcement learning. It allows an agent, a policy, to interact with the environment through actions and receive rewards and observations. And we are using Basilisk as that environment because it's fast, it has a C and C++ backend, a Python interface, flight-proven software, and modular configuration. So when we combine those two, we get BSKRL that's available on GitHub, and it allows us to use reinforcement learning with Earth observing satellites. So the agent that the policy we are using is obtained through reinforcement learning algorithms with deep neural networks. Basically, it maps states to actions, and we are using the synchronous proximal policy optimization algorithm, and we combine it with shields to guarantee safety. If you want more information about the training, you can refer to this work, also submitted to the GN&C conference in Breckenridge. Some of the advantages are that it works with complex constraints and dynamics, fast evaluation after training, and its robust variation in initial conditions and deviations in the environment. One of the downsides is the training cost, so in this case it took 12 hours. So how do we share information across satellites to perform collaboration? First, we are assuming free communication at all times across satellites, so they can freely communicate, they have enough bandwidth. And we are introducing two information sharing methods, completion and intent, and also two retasking methods, continuous and conflict, that I'm gonna talk about more in a second. And the policies, the satellites are running copies of the same policies. So, information sharing, we have completion sharing. In this case, what happens is that the action will be tasked, the action will be completed by that satellite, and then that satellite will send the list of the targets it imaged to the other satellites. In intent sharing, the action is tasked, but now it will share the list of intended targets to be imaged to the other satellites, and just then it will perform the action. For retasking, we have continuous retasking, where if any satellite completes an action, all satellites will retask. And in case of conflict, the action will be completed, the satellite will retask, and in the case that satellite has a conflict with another satellite, both of them or one of them will retask. And conflict can be understood as trying to image the same target as another satellite, or imaging a target that was already imaged, if that information is available. So combining these four methods, we get intent conflict, intent continuous, completion conflict, and completion continuous. We also added the no communication method as a benchmark. Now the performance of the methods. First, here we have the results for a long track formation with 0.1 degree spacing and uniform target distribution. And what we see here is that the light blue case, intent conflict, shows the best result. We have most of the rewards, we have highest rewards with intent conflict, we have zero wasted time, more unique images, and no duplicates. When we analyze continuous retasking, we see some chattering behavior and resulting in more wasted time. So wasted time is a way we are measuring the time the satellite spends in an action without completing that. So every time it retasks, it can pick the same action or another action, and when it picks another action, it will have wasted time. And we also see that completion leads to more conflict because it just shared information about the imaged targets after taking the action. To understand a little bit more those results, we can analyze the performance per satellite. That's the case here with reward and wasted time. So if we take a look on the dark blue and light blue cases, the intent continuous and intent conflict, we notice that intent conflict has a more balanced reward across satellites, while the intent continuous, the first satellite, has most of the rewards, has the least wasted time, while the other satellites don't have as much reward because they keep retasking. So they also have more wasted time. And the explanation for that is because the satellite in front of the formation will see targets first, will image them first, and then the other satellites will have to retask. If we vary the spacing across satellites, so here changing from 0.1 degrees spacing to 2 degrees spacing, and then a long track and city-based targets, we notice that the completion conflict case approximates the intent conflict case, and that's because with the satellites farther apart, they will have less chance of selecting the same target to image and will have less conflict. We also notice the same behavior if we vary the spacing from 0.1 degrees up to 30 degrees, also a long track formation with uniform targets. We notice that the completion conflict approximates intent conflict, and part of that is because it reduces the wasted time, it reduces the number of duplicates, and increases the number of unique targets. And again, that's because with satellites farther apart, they will have less chances of selecting the same target, reducing conflict. So some concluding remarks. We have that intent conflict shows the best performance, outperforming other methods. Intent sharing tends to reduce the number of duplicate images, while conflict retask reduces the wasted time. So when we combine both, we get the best performance in intent conflict. We notice that more spacing reduces the number of duplicates and wasted time. And training was not suitable for retasking mid-task. It means the continuous retasking cases where satellite will interrupt previous actions to select a new one. So future work can address that, having specific training environments for that. Also in future work, we can investigate auction methods, so satellites will decide which satellite should pick which target based on an auction, and also agent count agnostic multi-agent RL. Thank you for your attention.